Oh, okay. So we're about to get started here. This talk is about, if you haven't noticed yet, it's about reversing and exploiting embedded devices. But white is really like straining on the eyes. So for this talk, we're going dark themed. So the overview of this talk, I'm not going to fucking talk about everything here. In a nutshell, we're going to walk the software stack, then we'll go into like some hardware stuff. Essentially, in a nutshell, we're still exploiting software. It's just on an embedded device. So quick background, because, you know, obligatory, who am I, right? So I'm Elvis, or Black Owl. I respond to either or. I'm a researcher at Exodus Intelligence now. Got into this whole IoT stuff completely by accident. We'll talk about that in a minute. Side note for hobbies, I play games. Like if you're on like Counter-Strike or something, hit me up. I love shenanigans. I make like music, but it's really bad, so you'll never hear it. And then I'm also on CTFs all the time. I love CTFs. And that's about it. It's about me. So, hold on, messed up. All right, so let's start all over again. Okay, so talking about like how I got into IoT research and all that stuff. So I had a former coworker when I worked at Tipping Point, known as Headless Zeke, and he made a dumb fuzzer one day for his SOAP UPnP service on like some, I think it was like TP-Link or TreadNet or something like that device. And within 2 seconds, he found this like command injection like vuln, but it affected every single manufacturer who used Realtek, because Realtek was the developer of this binary. So it kind of triggered something in me. I'm like, I have all this hardware stuff at home. Like, let me just go home and just like pop something, right? But I did exactly what he did, and I failed. Completely failed. Like, fell on my face. I fuzzed everything. The HP daemon, the UPnP, anything with a socket, I fuzzed it. And I got absolutely nowhere. And it was so frustrating. So, what I did was I actually started looking at the binary itself. And what I found was there was a lot of like, I call it dirty code, because there's a lot of code in there that didn't need to be there. For example, there was like a USB mount function, and there was no USB port on the device. But, so for example, this particular endpoint, known as ZDI15, blah, blah, this was a simple command injection, but I never would have found it if I didn't disassemble it, because the API endpoint wasn't on the front end at all. It was completely hidden. So, talk about firmware. So, there's this researcher known as Craig, or DevTTYS0. He does amazing stuff. He's got this amazing YouTube channel now. It's got fantastic stuff. Like, I can't endorse it any more than that. He made this tool called Binwalk. And Binwalk, in a very, very high level, like actually, before I even go, who's used Binwalk? Hell yeah, that's awesome. So for the people who don't know, like in a nutshell, all it does, it parses binary files and finds the magic bytes within it and extracts the structure based on libmagic. So libmagic is exactly what it looks like. You start at like index 0 and you're like sig 0, the string or whatever is my magic bytes. So like for GIF, it's GIF 89A or something like that, 8987A. So that's how it works. It has all these like structures that are inside of it, and it just goes through using libmagic and extracts everything. And it's fantastic, and I love it, and you can modify it. It's all open source, great, whatever. So the thing is though, I came from like an x86, x64 background when it comes to exploiting. So a lot of these devices are running ARM or MIPS. So I don't know MIPS at the time. Like I didn't know MIPS assembly. So I'm like, all right, how can I teach myself this kind of crap? So that's when I stumbled across, and fair warning, I may butcher some names, QEMU or QEMU or whatever the hell you want to call it. So I found that, got into it, and started just cross-compiling everything and using statically built userland QEMU, or QEMU, wait, sorry, to see what was going on and actually debug the binaries and actually learn like how function entries and function exits work and all that stuff. So if you guys can't see this, so basically all I did was like, all right, I'm going to make a simple C function that's going to pass some arguments, maybe return some stuff, and then exit. So then when I compiled it, I use markers, like I use integers that I know, like 43, 43, 43, or capital C's, whatever, just to see exactly like where the code is and what I'm looking at. So off the bat, we initialize the local variable to 0. So in MIPS, there's a 0 register, it gets pushed into there. Over here, we have A0 being populated with hex 68 or hex 44. So we know that A0 is going to be the first argument to our function. A1 is going to be the second argument to our function. So in MIPS, it goes up to A4. After that, everything gets pushed onto the stack. So And then we know that once we return, the same offset of where we push 0 to, v0 is now being pushed into that. So now we know v0 is going to be it's going to hold our return value from a function. And then also same thing, second argument a1, because the first argument in printf will be the format string. So you can kind of see, just by doing some markers, you can kind of see very quickly like what's going on and how you can like just kind of learn this stuff on the fly. But the thing that was kind of like ambiguous was the last instruction there for the return for the D word was the LUI ORI instruction. So load upper immediate or something like that. So basically you just do what you normally do in x86, right? You just set a breakpoint, step one at a time, make sure step mode is on, and then you step one, and then you made sure the instruction was executed. You look at the register, you're like, all right, cool. So now I know LUI with 2 bytes, because, yeah, we'll fill up the upper immediate with 4343, and then at the end, if the space at the bottom is null, then I know that ORI is going to do the bottom lower 2 significant bits of bytes. So that's how we get our full D word into there, and that's how it gets returned. So cool. So learning assembly, cool. You can do it on the fly if you know C. But the thing is though, like taking a step back, we can do things a lot easier. A lot of these devices, like routers or whatever, use Linux and they use GPL. So if it's under GPL, the source has to be out there, right? So if you go online and type in like vendor A source code, cool. Like this device here, like fell onto that. Vendor B, cool. I have a smart TV. I don't know why, but hey, source code for it is right there. You can download it. You can actually make your own binaries for these things too. And then vendor 3, same thing. Just look for the source code and it's right there. Complete tarball, everything. It's beautiful. But the thing is though, a lot of these, at least recently, they're coming with like precompiled binaries inside there, so they're not under GPL for a lot of the binaries now, which is sad. But to talk about hardware a little bit, because I did talk about software. So I did have, in past talks, I've talked about like different tiers of like hardware to buy for your own like home lab. And it's not really needed. Like the tools I normally use like 99% of the time whenever auditing a device is this. I use an FT232H breakout board by Adafruit. You can buy it for 15 bucks. It's pretty cheap. The same thing, it would be the Shikra. That's a little bit more expensive, more user-friendly, but still same processor. You can get the JTagulator if you want, or if you want to go the cheap route, like I did, you can get an Arduino Nano and just put JTag enum on it and have yourself a $5 JTagulator just without the voltage adjustable voltage regulation via software. And then a logic analyzer, I use that whenever I'm probing pins. I have no idea what the hell they're doing. I bought mine from Soleil, pretty quick, awesome. And then just your run-of-the-mill multimeter, soldering iron, solder, you know, desoldering pump and wires and all that stuff. So like, just adding these all up, if you bought everything brand new, like you would probably spend around 300 bucks. But honestly, you just need the FT232H breakout board. You can make your own JTagulator. You can do a lot of these things cheap. So don't be shunned away by the price. You can do things for like 50 bucks if even. And that's all you'll ever use. So, okay, cool. So now we know like the hardware we're going to use and all that stuff. So let's actually talk about some of the interfaces that are available on hardware stuff. So there's something called UART. And if you're looking at a device and you go, I wanted to see what that board looks like, but I don't want to open it up because I don't want to avoid my warranty. No problem. Every single wireless device in the US has to go through FCC qualifications. So if you look on any device that's wireless, whether it be Bluetooth or whatever, it's going to have an FCC ID. Take that FCC ID, and you can go to FCC's website. There's something called internal photos. Open it up. Cool. So we have the complete PCB front and back, like sometimes super zoomed in, like that Broadcom. I can make out like the parts and all that stuff, which is fantastic. But at the very bottom, we see like 2 groups right there. And if anyone's ever like played around with some hardware stuff, you'll recognize that those like series of holes, or what you can say, it's usually UART, and the one below is going to be JTAG. But that's a standardized port. So I looked at it, I'm like, oh, cool. So now let's actually open it up, because I actually may have UART or something. So now I feel more confident about opening up the device before just blindly opening it up and screwing everything over. So one thing I really want to stress, and I screwed up with this, and I don't want you guys to make my own mistakes. Find ground first if you're going to do any of this stuff. I've blown up so much crap just by like dicking around. I'm like, all right, this is not working well. So yeah, so finding ground. So remember, find a common ground point. Check it out. Two modes that one mode that a lot of people use is continuity mode, and I have some slides later on that will tell you why not to use that and to use resistance instead. So exactly, why not to use continuity mode? So this is me moving the dial, so there's some noise. This is the output from my logic analyzer. So the multimeter in continuity mode is pumping out 1.6 volts. Which is not that concerning, but you may power up some stuff you don't want to power up or whatever. And then resistance mode. So resistance mode, there's no voltage, right? It's just resistance. So when you find ground, the resistance will be 0. So that's how I've been doing it. And it's been working great. So to talk about UART a little bit, again, it's super simple. It's just receive and transmit, and then the clock is determined. There's no clock. You have to pre-do it. So you have receive the transmit, transmit to receive, just like you would like a phone call or whatever. Then your common ground, don't forget common ground. So, so the thing is though, like when you're looking for these UART interfaces, you don't know the clock speed, you know the baud rate, right? And I hate brute forcing my way around because it's so slow and it's noisy and it's just unreliable in my opinion. So this is the Soleil hooked up to the UART interface. And this looks kind of lame, but don't worry, we're hackers. We can do CSI enhance, which we do. And we notice that what we're looking for is the least significant, the shortest width bit when the falling edge and the rising edge happen again. You don't have to find the exact one, but in this case, it was 8.8 microseconds. So all we have to do is take 1 second over that time, and we get our baud rate. So, and also the Soleil software to have like, protocol decoders. And I'm like, all right, like look at this signal. It's a serial interface. Here's the baud rate that I calculated. Tell me if it's right. And it'll come back and it says, yeah, this particular sequence right here is the word start with the space. Cool. So now I know the receive, the transmit. I know the baud rate now without having the brute force. So now I can just pop it up. And also to round this off, it would be 11,5200 for this particular device. So cool. No need to brute force our way around. So let's talk about JTAG now. So JTAG is fantastic. It's a really great it's a really great tool for people to like debug their own hardware or find issues really fast. It's a fantastic interface, but it provides you so much like abilities. You're practically God mode at this point. But just to give you guys like an idea of like to show you how it actually works. So you have something called a tap interface. And you have all these things like TMS, TCK, which means mode select, clock, reset, in, out. Pretty simple. So in the next slide here, basically TMS is going to influence this state machine here. So if we start where the arrow is pointing at the 1 there, once the clock happens, TMS, if it's high, it's either high or low. It's either 1 or 0. If it's high, it'll go over to the next one. Next clock happens again, it goes over to the next state based on what TMS is. So this is basically in a very high level how you interact with the JTAG state machine. Later on, I'll show you like tools like OpenOCD to actually communicate with it and show like what it's all about. So if you don't have like UART or UART's like password protected, you don't have JTAG, but you're kind of running out of ideas and you can't find the firmware online. These things are fantastic, like flash chips with external leads are amazing, but nowadays you'll see BGAs and BGAs are the devil. But so this particular device was the MX25, you can read that. Basically all I did was I Googled it, fantastic, found the data sheet, dope. So now we know the exact pinouts, we know our chip select, our hold, our power, our ground, and all that stuff. But the problem is these type of chips are like, I don't know, like it's a master-slave type of situation. So when a CPU selects the chip, nothing else can communicate with it. It's a 1-to-1 ratio. So when you are going to supply power to this thing, if you're not going to take it off the board, there's 2 things you want to be wary about. One, if you turn it on, well, actually supply power to this, you may turn on the processor. Processor may select the chip, and now you're screwed. So the next thing would be find the reset pin for that processor and ground it. And then turn it on, because now that CPU will just sit there and not do anything while everything powers on. You can communicate to the chip, you can select it, rip everything, and happy days. So this was just another thing to, like, when you're using the logic analyzer, you kind of want to, like, line things up, like, all right, got the clock, I got input, output, like, how is everything, like, working? And, like, this is just, like, a random, like, image from the data sheet, just showing you, like, the input, output, and the clock, and what shift in, shift out. Very, very simple, straightforward. whatever. So this is like a capture also of the chip. So we see the clock at the very top, clock, clock, clock. And then we see hold, and the hold wasn't doing anything, and we got output, we got one little line. I didn't throw the protocol decoder on this, so I don't know what actual opcodes are being sent, but we see chip select, donk, goes down. When chip select is down, that means the chip has been selected and nothing else can talk to it. Cool. And if you, like I said, if you don't want to desolder it, there's other ways to like probe the chip. This is what's known as an SOIC 8, because there's 8 pins. It was $5 on Amazon. It's very good. It's great. You can use little test probes, whatever you want to use, right? And these things, you'll run into these. These are, like, what was it, like parallel NAND flash. And these things are freaking, like, oh, they're so hard. Like, if you get a corrupted chip like this, have fun trying to find a file system. Like, it's pretty much a pain in the ass. And ripping this thing, this was like, what was it, 2 gigs? And it took about 4 hours with an FT2232H. There's actually a great talk, forgot the researcher's name, but it's online, about how to extract images from NAND flash. And that particular breakout board, like again, Amazon, $10. Like, awesome. I didn't have any female wires, so I used my breadboard, which is kind of a bad idea because it introduced a lot of noise. But I just want to take a fancy little photo of how I hooked it up. And there's like, you know, all these tools out there that are Python compatible, like Python libraries you can just download. And this one is called dump flash. And I was like, all right, just give me everything from like, you know, the hardware, like the ID and all that stuff. What is it? So we can verify. And it's awesome. This stuff is like super simple. But if you are going to run binwalk against it, like don't do that because you'll end up with like 200 gigs of just crap. So you are to potentially find offsets. So it's talking about exploitation a little bit. So there are times where you look at debug. Well, there's times where debug code or signal catchers are like compiled into the binary itself. So cause of the crash, I know exactly where my offset's now into my string. That is badass. I don't need to like cross-compile GDB and throw it on. I know my offsets right off the bat. I just don't know the other registers in my control, but you can just look at it by the exit function, the function exit, sorry, to see what registers get popped before it returns. So pretty simple. You can analyze the crash with the assembler, like I just said. You can also emulate it. If you look at the code, you can put it in QEMU and just kind of like, you know, do it on your own desktop pretty quick. So crafting the exploit. So this was x86 versus MIPS. So x86, this is a simple like stir copy from argument value 1 into a stack buffer and then printf some stuff. Same code, just copied over. Well, cross-compiled for MIPS. So we see our exit, like the function exit, right? That's the one thing we're looking at. So we see leave and we see return. So we know that EBP and ESP will be switched. And then also, what was it? EBP plus, or EBP gets popped. Either way, we do know that our frame pointer and our instruction pointer will be in our control. And same thing over here where we load a word from the stack into RA, which is our return address register. And also just to point out, just because there's a return address register doesn't solve stack-based buffer overflows. So, and then the other one, popped into the frame pointer off the stack, and then jump register RA or return, right? So, same thing, but for ARM. And it's got to load. So, same thing, is that we restore the stack before going back to where we were in the other function, and then we pop 4, so FP and then PC. So, pretty simple. So, like we said, we can predict stuff, we can look at it and go, all right, we're pretty much like in line of what we've done before. If you've ever done smash a stack stuff or CTS on x86 stuff, it's almost exactly the same. It's just a different like language, right? Obviously, but so yeah. So we can debug it, all that stuff, blah, blah, blah. So crafting the exploit, because no one likes just a crash. At least I don't. If you get a crash, take that shit all the way, man. I hate when people just stop and go, oh, code exec. You didn't prove code exec, you proved corruption. Anyways, I'll stop bitching. So one thing that's great in libc for x86 is that you guys are just so spoiled with gadgets. Like, look at all the jump ESPs. There's so many of them. Like, why is that there? MIPS. Go fuck yourself. That's basically what happens in MIPS. So when you're doing basic like stack buffer overflows and the stack is executable, you have to ROP. And I'll show you exactly that. So I recently published an exploit against Belkin. It's a 0-day still, and we'll be talking with that during the demo. But yeah, this this whole sequence here of the 4 gadgets, it's literally A, me sleeping for a little bit, and then me trying to get the stack pointer into a register that gets called. That is it, because no one likes hard-coded stack addresses for return addresses. So one thing that was getting a little frustrating, and like same thing with x86, right, was the freaking null bytes. Holy crap. And this image does not load right now. I don't know why, but normally he throws the machine, and that was me afterwards. I'm like, dude, fuck this. Like, I'm done. But then I started thinking about it. I'm like, you know what? We can XOR everything, right? We just XOR. So I use Radari. I love Radari. Like, those guys, amazing. And so they have this, they have an assembler called Razm2. And so I was like, all right, well, let's see if I can XOR something and see what the opcode is. There's no null bytes. Great. So now we can create like our own encoder decoder stuff if we want to using Razm, and we know that it doesn't matter with null bytes because we can just XOR it. So, oh yeah, awesomeness. So like I said, in a nutshell, we can use the same techniques from x86. Use Razm2 to assemble your instructions for like shell coding, or even just like cleaning up the stack or something like that. Like, so what I've had to do before was when I returned to the stack, my stack address was like a little bit above. So going back down, when it read that address as an opcode, it was an illegal instruction, it would kill it. So instead, I found out that no operation is 4 nulls and MIPS. So I just XOR a register, and then I store it based on where that ret address was. So when it hits there, it's now null, and now it just goes through cleanly. Great. So, like in a very, very like, you know, high nutshell, you can say, you grab your libc base address, and a lot of these devices, I've seen that ASLR is completely broken. I've seen that randomized VA space will be set to 2, but reset the box, crash it, whatever you want to do. Those libraries are being imported, stay at the same address the entire time. So if you don't need to leak anything, you know, you can just grab the base address. If it's on the Linux machine, just do like cat the process maps, and you'll get all the libraries right there. And then you just take the base address of the executable region and just add your offsets based on what Radari tells you. Find your offsets, craft your shellcode. You can test the exploit in QEMU. The problem is when you get this with the connection back, the execute call just like dies and the whole thing's side fault. It's kind of funny. But you can test it in there before moving it over, because all you have to do is just change the libc address. That's all you have to do. And then afterwards, profit, awesome. So this was an example. So I made this tool that I'll talk about towards the end. It's kind of like a learning tool, you can say. It's called DVRF, because we need another damn vulnerable thing in our community, right? So I created that. So what I created was what's called damn vulnerable firmware, router firmware. And it's an actual router image for a Linksys device. And you can install it, and there's vulnerable binaries inside of it. Then you have to use UART to get to it and all this cool shit. So basically, all I'm showing here is that I emulated my exploit first. It worked, went over into the actual device, ran it again, just different padding. So don't worry about that. It's still the same offset, still return address. So it works. But one thing I want to advocate going forward, and I kind of bitched about it a little bit, is that this kind of shit needs to go away. We need to make POX great again. No more DOS POX, and fucking vote for me for your next exploit. Don't worry, I will not build a Faraday cage around the devices and make the vendors pay. Don't worry about that. So yeah, I guess demo time. Cool. So I've had demos in the past where I've like done a balaclava and all this stuff, but for this talk, for this one, I wanted to actually show the O-Day stuff that I recently did with Belkin and show you guys how I found the vulns, and you can go home and do this shit too and find your own vulns, right? So, oh yeah, 0-day edition. I totally forgot. Anyways, so I'm going to power on the device here. So the device, just to hold it up, it's literally this little repeater. I bought it when I was like living with roommates and I was upstairs, needed to extend the range from downstairs because there was no wireless. So then this is the device I just picked up one day after, you know, when Ricky did his whole like command injection thing. So this is the device. It is now powering on. And so what I found was a few things. So a lot of people, and they're like, oh cool, you found a router vulnerability. Who cares? Like, you can't hit it directly, or, you know, who would be stupid enough to have the WAN like listen on the internet for this service? Doesn't matter, because the way I hit this is via cross-site request forgery. And also what's great about these things, hard-coded DNS names. So you can do your cross-site request forgery where the destination for this one's belkin.wrx. You don't even need to know the IP address. So you just set your cross-site scripting somewhere, the web browser will evaluate it, internally will resolve to the IP address of this, and then we'll own it and you get a shell. So awesome. So we can do buffer overflows based on, like, via cross-site request forgery, based on what it is. So don't be discouraged by going, oh, who cares? Like this, the socket is like, I had to be internal or adjacent. Don't worry about that. There's other vectors of attacking these things like remotely. So I think the device is up now. So, that looks horrible. Hold on. That looks horrendous. Let's change some colors. Let's see. There we go. Can you guys see that? Or should I make the text larger too? Text larger? Yeah. Enhance? Alright, I'm enhancing. I'm not enhancing. Why am I not enhancing? It should be... Yeah, Control Plus, right? Yeah. Well, it doesn't like it. Sorry, guys. Shit. This sucks. 1 second. Cool. We'll just make it bigger like that. So this code is on ExploitDB. It's on zeroday.today. It's everywhere. I released it last month because of the timeline here. I disclosed the vulns earlier this year to Belkin, and 180 days later, it was still not patched. So I ended up just releasing it to the public because I think that's kind of sucks, to be unpatched for 180 days. But the problem was it wasn't with Belkin, actually. I actually talked to the people there, and what happened was these type of devices are manufactured by third parties. So Belkin had no control over the firmware off this, so the third party just sat on it forever. So that's basically why it got unpatched and all that stuff. So when you're disclosing these type of vulns to vendors, like, sometimes you have to ask them, like, hey, is there like another manufacturer in the play? Like, why is this taking so long? Because, like, to be honest, a lot of these vulns, like routers or whatever, take a very long time, except for the Linksys brand. It's a 30-day turnaround. But a lot of these take 180 days or even more to patch them. This is still unpatched. It's crazy. It's just simple sprintf. So basically, remember what I said in the beginning, like learning assembly, all that crap, yada, yada, yada. So basically, all I did was I looked online and I found the source code for this device, which is right here. You can compile it, you can do whatever you want, and just went into, like, what was it? I believe AP, and BOA is the HP daemon, and the source, and then so this is the complete, this is the daemon that I was looking at for this Belkin device. It's called BOA. It's an open source web daemon, whatever, but they program a lot of these endpoints, API endpoints themselves. So this one was called, like, what was it? Form set. So this particular function, form set language, you can hit this remotely. And so you look at it, you're like a bunch of, if, or stir compares, blah, 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 blah. But then if you look at this thing, you're like, all right, if this thing dies out, it goes to error. All right, what's error? Error over here will take the web page parameter that you post to it and sprintf %s into a stack buffer of 100 bytes. Dope. So now all we have to do is just cause it to error out, and we have a stack buffer overflow. Pretty simple. Took 2 seconds to look at it. Like, if you download some firmware stuff and just like search for like your basic, low-hanging fruits for C function, start copy, sprintf, all that crap, you'll find a lot. And it's kind of crazy, but sometimes you can't hit the vulnerable code. So this is how I found it originally. So one thing I was looking at too, a lot of these endpoints require authentication. No one likes post-auth like vulns. Like who fucking cares, right? Well, not entirely, but still. So I was looking for something that was available on the front end, and it was non-authenticated, because a lot of these endpoints, except for this one, require authentication. So this one does not require authentication. Cool. So now it was about actually chaining stuff together. So what sparked the idea of cross-site request forgery to attack this buffer overflow in this web daemon was DEF CON for IoT Village. And they were like, yeah, if you can chain like multiple vulnerabilities, you get like so many points and all this stuff. And I was like, oh, that's fucking cool. So I So all I did, so let's go back to the script. So all I did here, so just the very bottom, it's literally, so I'm writing a JavaScript file called a.js, and it gets picked up. There's a function in there called getRect, and that when it gets picked up, it wrecks the Belkin device. Awesome, and I'll demo that in like 2 seconds. So let's go with the demo, right? So if I go to the device itself, like I said before, I don't even know the IP address, but it doesn't work, right? Let's see here. Cool. Like I said, Belkin.wrx. I don't even need to know the address of the device that I'm attacking, thanks to hard-coded DNS names. A lot of manufacturers are guilty of this. So I was looking at this, playing around, yada, 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 and you see these things up here, which is form set language. So I was like, cool. I did a Wireshark capture and saw the endpoint, saw everything, and I was like, cool. So I triggered the vuln, and what I did was I'll talk about this when I go back into the slides. I downloaded something called BuildRoot, and you can, cross-compile a lot of these tools like GDB, GDB server, strace, whatever you want. You can statically compile it too for your device. So I made GDB, cross-compiled it, cross-compiled GDB, statically compiled it, put it on the device because it has wget on here, and then attached it to the pin and started just crashing it and crafting my exploit like that. So just to get this going, let's see here. All right. All right. So all we need to do now is go into our thing, and then we do this. I do -H because I forgot, and also I remembered that I foobarred this for people who were gonna just download it right. So let's just fix this real quick. And I apologize for the guys who use Emacs or whatever you want to use. So okay, so I didn't just we're about to exploit this stupid thing. So yeah, so let's just do it, right? So -S would be our connect back. So the shellcode that I'm executing is literally just a connect back socket and dupe2 standard in, standard out, like very, very basic reverse shell. And the shellcode I actually found via a project that I was notified on Twitter called Bowcaster. So that's there's a lot of these Metasploit-ish type of frameworks coming out now for embedded devices, which is really cool. So 206.2, 192.168.206.2, and then let's see here, 102. Oh yeah, we'll just do Belkin.wrx. So basically, what this is going to do now, and I also need to sudo it because it's going to run a HTTP daemon on port 80 and Hunter 2. All right, cool. So basically, now we've made our JavaScript file. It's sitting there. It's called a.js. It's right there. You can see it. It's beautiful. And also, once we get shell, we can also bypass the authentication stuff. So one thing also is once you get shell, see what you can do. What if you wrote a file to certain locations? What can you actually do after you get shell? Because this is a router. All the network stuff runs through it. So you can do TCP dump and all that crap. It's amazing. But either way, so if we go back to the device, not Twitter or eBay. So we go back to the device, and actually, crap, it's actually picking up something. All right, cool. So let's. All right, I got shell, but that was that was by accident. So the SSID on there is cross-site scripting as well, just to make it funny. But so these things though, if I clicked security, I need a password, right? I need something. I can't do much. I'm all right, cool. So what we can do, like I've said before, let's kill that. Bring it back. Address is already in use. No. All right, 1 second. Sorry, guys. Come on. Is it still running? What was it? Sorry. No, it's not. What the fuck? 162. What the fuck, dude? Why isn't this working now? What did I do wrong? There we go. Cool. Now it's serving. Whatever. Just had the socket had to die. Sorry about that. So okay. So let's just finish this, right? So I go to my awesome, dope GeoCities website. It's pretty cool, and it's got marquees and shit. And it didn't download it. God damn it. God damn it. So fuck it. We'll just do it the original way. Fuck it. We'll do it live. And then in like 5 seconds, 3, 2, 1, we should get a shell right about now. Maybe, kind of. Come on. Yay. Cool. We get a shell. So in this part of the script here, it's kind of hard to read. Actually, let's move this to another. No. So right here, I had this echo command. So like before, I said that we can't do anything. So what I saw was when I logged in was that I was writing a file, and that file contained a MAC address. And the MAC address basically it will just read it and put it into a trust zone and just say like anyone with this MAC address can, is authenticated now. That's how it keeps track of sessions. So if we just paste that in there, we now have access to everything. Security, there's my password, it's pretty funny. And then like the cross-site script and all that stuff. So we can actually remove it, and just like intended, we can't log in. So that was the demo, very, very basic. I just wanted to show you guys how easy this is to actually find stuff. It's 1990 again, but in the year 2016, it's Back to the Future, dude, but a really bad remake of it. So yeah, let's go back to the talk. So thanks for, sticking around for that. I appreciate it. I know it was a little dry, and that's the first slide. This talk is not going all that planned today. I apologize for that. All right. And then starts. Okay. So the difference is x86 stack-based buffer overflows are really, really simple to exploit when the stack is executable, right? Like super simple, basic 101, jump ESP bullshit, right? Super simple. You don't have to like ROP or anything like that. And also assembling instructions and stuff is pretty easy to do without null bytes. And yeah, so it's pretty straightforward, right? MIPS, it's the same idea. The stack's executable and all this stuff, but we just need to get to the stack somehow. We need to get the PC into the stack somehow. So, like I said before, in libc and stuff like that, there was nothing that I could just jump SP or move SP into like T9 and call T9. It wasn't working like that at all, and I had to ROP because it was one instruction at a time. It would be like move A0 here and then move, whatever, like maybe A0 and S0 and S0 to T9 and then call T9, like that kind of shit. So, like, it's a little bit different, but if you've ROPed on x86, you can ROP on MIPS. It's the same crap. It's very straightforward. It's all about the function exit, right? So it's all about just popping everything and you control everything. So, and also when you're doing this stuff, you can like translate stuff. So like on MIPS, you have something called jump in link register. It's the same thing as call. All it does, it takes where PC is, adds A to it, and puts it into our array, and then we'll go into the function, then returns. Cool. So like I said, in a nutshell, they're essentially the same. Don't be like intimidated just because it's a different architecture. If you've taught yourself x86, you can teach yourself this shit. Like I am just some random kid, so if I can do it, you can do it too. That's how I see it. And then ARM. ARM is, I'm still learning that one. That was kind of a bastard. There's so many variations of ARM. ARM v5, v7, there's Cortex, there's all this crap. But the instructions are still kind of the same. But when you look at the exits, you'll see like pop and then like a shit ton of registers, but it just goes one at a time. And also, be mindful, these processors have different modes. So in ARM, you have thumb mode, which is a 16-bit instruction length, and then you have ARM mode, which is a 32-bit. And also in MIPS, you have something called MIPS 16E, and some devices, which is the same thing, which we can go into 16-bit or 32-bit mode. And the way that works is very, very simple, straightforward. Like on ARM, it's called, like jump in exchange or branch in exchange, I believe it's called. But basically what happens is if you jump to an odd address, it switches over into thumb mode and subtracts 1 and starts there. So if you jump to like 41, it will go into thumb mode and start at 40. That's how that works. And MIPS as well has something called jump in link exchange. So link exchange will always switch the modes. So that's pretty straightforward. So talking like earlier with JTAG and all that stuff, I've seen people talk about this kind of shit, but not a lot of people have actually like played with it. So this is the JTagulator, like, you know, I've talked about before. You can also make your own, pretty cheap, but this thing is pretty badass, right? It's a little expensive, but all I did was I have a little Arduino board with the JTAG interface on it, hook up the JTagulator, JTagulated it, and started learning this shit, right? It's very straightforward, very, very simple, especially with the JTagulator because everything is simple with that thing. So what you can do afterwards, though, is that so when you have the JTAG interface and you've identified everything, your clock, mode select, input, output, all that stuff, what do you do next, right? So with these processors, like these little FT232Hs, these are your interfaces that will communicate to the things. You can also buy like J-Links and all that stuff, but they're a bit pricey, and I'm cheap, $15. So there's this open source software called OpenOCD. Who's here has used OpenOCD? Okay, so like a few of you guys. All right, so OpenOCD is literally just a way to talk to different processors, JTAG state machines. That's all it is in a nutshell, like very, very high level. So what you have to do is that all you have to do is say like the FT232H FTDI is my interface, and then there's so many configuration files that you can find that come preloaded with OpenOCD. And just because you can't find your processor exactly on there, look for something that's like it, same processor type or whatever, and those OpenOCD configurations should work. So once you have OpenOCD up, what do you do next? So what you can do is you can attach GDB to it now. So now we are the processor. That's what JTAG is. We are the processor now. We control everything. So you can do GDB server to it, and you can set like watch points, break points, whatever you want, but now you have the full actual hardware of RAM. You can use it all. It's awesome. And this is real useful when you're exploiting real-time devices that don't have a command line interface like a lot of these Linux embedded devices have. So this is very useful. If you have JTAG, like, you should jump up and down because you are basically God and you can do whatever the fuck you want, and it's awesome. And then there's also an interface for OpenOCD that default is open on 4444. And this is where you can like communicate, like, I need to initialize JTAG, I need to measure the clock that I'm at, maybe just halt the processor or maybe reboot the device. And it's great. It's beautiful. So I love this because now you can set up a literal like hacking bench where it's just one machine that you connect to via like SSH, and all the hardware stuff is just connected to it, and you can use software to just switch by it, and it's fantastic. So okay, that's enough of that boring shit, right? So to wrap things up, I'm going to do a quick little probe, I guess, of my little project. DVRF, or Damn Vulnerable Router Firmware, like I talked before. So like I said, I've already gone through all this stuff. It's basically just a way to teach yourself, or if you're curious about IoT stuff or just embedded hardware, just get into it, right? Like, you know, just play around. Like, you know, you don't have to sacrifice things to the, you know, overlords or whatever. Like, you just download this, fuck around with it, and if it's your thing, cool, now you can go out and buy some stuff and actually start learning some more. So, and also to help like IoT developers or whatever, just look at shitty code. Like, don't program like me, dude. Like, that's horrible. So, you can download it on GitHub. It's on my previous employer's GitHub, Praetorian. I don't care where it is, to be honest, as long as people can get it. So you can download it there. It's also all over the places. People have been doing blogs on the different challenges that I have on there. I'm doing write-ups. So it's great to see the community actually using this and learning and, you know, paying it forward and stuff. These references are just very basic. So like I said before, the hardware, this will be online because you guys can't see that shit, right? But to wrap it up, as Dual Core once said, first we drink all the booze, then we hack all the things, and then we backdoor the firmware in anything you bring, because regardless of the service protocol encoding, connected to the internet, and someone's going to own it. That's the end of my talk. Any questions? Either I did really good or really bad, because there's not a single question. Oh, there we go. Yes. So the question was, have I seen anything that's like would kick out a debugger once you attach to it? No, I haven't seen anything like that yet. But yeah, so I haven't seen it at all. So there shouldn't be a worry there as of today. Maybe next year you'll start seeing that, but as of today, no. Yes. So the question was, have I hacked anything like a console, like a PlayStation or something? I haven't personally played with it, but they're just x86 right now process devices, so it's just a standard PC at that point. But no, I haven't played around with consoles yet because I've been too busy dicking around with routers and stuff. But maybe in the future I will, because stuff like Xbox One or whatever was pretty interesting to me, but I just haven't sat down and looked at it. I'm sorry, I couldn't hear that. Can you speak up? Yeah, I believe the PS2 is a MIPS-based processor, but yeah, so that would be pretty close to like what this Belkin device is a MIPS processor as well. But yeah, I would say just go home and just open it up. Like, yeah, I haven't personally played with it, but that shouldn't deter you. Like, go home and just do it, dude. And also just a quick probe as well. If you're worried about like devices and breaking them and all that shit, you can go to Goodwill and buy used routers for like $5, and it's awesome because you have all these different brands. I don't know where they came from, but I'm not gonna question Goodwill. But you have like, you have like Comcast branded devices and Verizon branded devices. Like this came from the like straight up from like Verizon, whatever. I'm like, oh, this is so dope. So like, go to Goodwill. Like they're cheap devices, $5, and you break it. Who cares? Just get another $5 devices. Or hell, even ping me. I have devices in my closet I'm willing to just give away because I don't give a crap about them. But but yeah, are there any more questions before we wrap up? Yes. I'm sorry, can you say that again? Oh, yeah, so the question was, my slides are going to be available. Yeah, they'll be posted online. So I'll have to coordinate with the GrrCON guys and see how I can get that out to you guys so everyone can get it. But yeah, so yeah, the question is yes. The answer is yes, yep. Any more questions before we leave? So yeah, I have. So that's where the OpenOCD stuff came into play. I have done real-time devices. So the last one used a Cortex M3, and it did run RTOS. It wasn't VxWorks, but I just used OpenOCD and the exploitation stuff exactly the same. Well, what's better about that is that everything is static in those things. So there's no jumping around or whatever. So when you're doing real-time devices, it's kind of more exploit-friendly, you can say. But just because, like I said, just because you don't have a full-blown operating system or processor with a memory management unit or anything like that, don't let that deter you, because it's just the same thing. It's just you have to kind of attach to it in a different way using OpenOCD. But once you have OpenOCD, you can dump firmware and stuff. You can dump everything. So it's great. So what's great about that too is that once you have OpenOCD running, if you have IDA per se, you can attach IDA to it, and you can set breakpoints like that too. So OpenOCD and IDA work great together. But yeah, so that's kind of like, yeah. So I have played around with real-time devices. All right, I'm gonna say that we're done with the talk now. Thank you for coming, and enjoy the rest of the GrrCON. Happy to be here. This is great. Thank you guys.